everyone, welcome back to the Lee channel. In this video, I am going to go over a problem in your homework on graphing position, velocity, and acceleration time graphs. As you can see, this is a pretty long question. I'm actually going to break this video into part 1 and part 2, where you can find the link of part 2 down below if it's not already on the side. In part 1, I am going to do all the acceleration problems. So these ones, not that one, and complete the acceleration time graph. I will do the displacement average velocity and the position time graph in part 2. Starting with the first part, the velocity time graph, we are given the graph here. We are asked some questions on the acceleration, the displacement, draw the acceleration as well as the position time graph. So let's get started quickly. If we take a look at this velocity time graph, many of you will be tempted to think that the object is traveling back as not moving and then moving forward again. In other words, confusing your velocity time graph with the position time graph. So we have to be very careful. This graph is telling you how fast or slow your object is moving and in which direction, in the positive or in the negative direction, which I will say this is, let's say the positive is forward direction, and then in the negative direction where your graph is going below the x-axis, going backwards. When I get a graph, usually what I like to do is I like to visualize what your object is doing. And since maybe you've played with the moving man simulation, the FET simulation, which I will also include the link down below, I've put a little rough sketch idea for you to look at. So if you can't see my cursor very well, I'm pointing at the velocity time graph. This is a very rough sketch. What I've done is I've adjusted the values so we can easily see this on the screen, and also for the little man to be able to use the screen without crashing to either wall, if you know what I mean. But anyways, I've shortened it so that you get the idea. I put him all the way at this end so he gets all that space to move around. And I'm going to press the play button for you to look at how he is moving so you can visualize it. Here's a velocity time graph. It's going down, and then there's a straight line, and then it slants upwards again. So let's see what he does. So pay attention closely to what he does, and I'll narrate as we go. So look, he's going back. Ooh, he's speeding up. And he's not really, he's kind of going at the same pace, and then, ooh, he's going backwards. Bam. Okay. So we can play that again, and I'm gonna slow that down. And I want you to notice something. Is as he's moving back at the beginning, so from there to there, notice that that's a little bit too slow. Let me try that again. Play back. Okay. So whoop. Notice that he was speeding up, and then if we compare that with the velocity time graph, notice the red line is going down, indicating that he is going backwards in negative direction, but his speed is increasing. Now let's see what he does in this stretch where on the velocity time graph the line is straight. Notice he is he's not really changing his speed. He's going at a constant speed there. And it makes sense because on the velocity time graph, the line is straight. His velocity is not changing. And these numbers, just ignore these numbers. They're just rough estimates. Okay, now this is the part where many of you think he's going to start moving backwards, where the nick is in the graph. But be careful, the line is still below the x-axis. His velocity is still negative. He is still moving backwards. But watch what happens to his speed. Oh, hey. Notice he's slowing down. But this is where it gets interesting, where you think, okay, is he going to continue to slow down forever? What happens until he can't slow down anymore? Well, then he stops. He stops at this part here where your red line crosses the x-axis, telling you that velocity there is 0. So let's play that. do. Oh, he stopped. Notice that right there, he just stopped, and now he's moving back again, but now he's increasing his speed in the forward direction. Okay, so now I know that you can't have a simulation on your test or when you're doing a quiz or anything, but hopefully this will help you read graphs as you practice more, etc. Also, you see the position as well as the acceleration time graphs. Don't worry, I will go over how you can get at that without having to use a simulation. You can always use a simulation as a check, but that's up to you. Okay, so now we kind of idea what this guy does, and just to play that back again, maybe a little faster speed there. He goes back, speeds up, goes at constant speed, slows down, stops, and starts to move forward, increasing his speed. So that's kind of what he's doing. In fact, I probably answered this question down here, which we can touch on later. Okay, let's start with the A. What is his acceleration from t equals to 0 to t is equal to 2? So using my blue pen, that is from here to there. Okay, so before you do any of these calculations, I want to write a little bit of something, so a little bit of a trick for you to help you remember something. A position time graph, which I'm going to write as dt for displacement. It's just easier to visualize. D as in displacement. VT graphs, AT graphs. So we have these three graphs, and you're expected to be able to interpret any of these three and be able to convert from one to another with enough information. So how do you do that? Going from a displacement to a velocity to acceleration, as you're moving down, as you're going from a displacement to find your velocity, and from a velocity time graph to find your acceleration, you are grabbing the slope. So the rate of which something is changing. Because you think about the meaning of a slope, this is how velocity changes over time. So that's the slope. On the displacement time graph is how your position changes over time. You're grabbing the slope. You're always dividing by time. So here it's like going from m and from your meters, and you're dividing it by time. For velocity, you're taking meters per second, and you're dividing by seconds to get meters per second squared. So you're always looking at it as a rate of change, okay? Vice versa, and we're not gonna need this for this video. I'll come back to it in the second part, but to go backwards, to go from to read acceleration time graph to find your velocity, or change in velocity, and going from your velocity to get your displacement, you are going to find the area. And why is it you're trying to find the area? Well, I'll talk more about it, but essentially what you're doing is you're trying to find how far or how much something has changed in this amount of time. You're looking at the rate and using a rate to multiply it by some amount of time to get how much you've achieved, essentially. I'll talk more about that later. But I'm going to write this little note, which you're multiplying color, you're multiplying by time in units of seconds, and I'll come back to that in this second video because we're doing acceleration in this video mostly. Okay, so now we have this little diagram to remind ourselves. Going back to A, we're trying to find the acceleration from t equals 0 to 2 seconds. We're grabbing the slope from here to there. So we're looking at this slope right there. So I'm going to write the slope. And I'm gonna write it in a more kind of a quicker hand. You might remember slope as y2 minus y1 over x equals 2 minus x equals 1. And you could do that. If you want to grab this coordinate and grab that coordinate and do that, I'm going to do it a much faster and maybe more intuitive way, depending who you are. Rise over run. But you have to be careful one thing. When you're doing rise over run, look at this graph. The slope, you're sloping downwards over time. So in fact, you're not rising, you're actually dropping, you're going down. So your rise value is going to be a negative value, not a positive value, going down. So it's going from 0 to -4. And I'm going to write -4 here. And don't forget your units. -4 meters per second. What is the run? how far are you running? You're going from 0 seconds to 2 seconds, which is just 2 seconds. And that's gonna equal 2 divided by 4 is equal to 2. Don't forget your negative sign. Meters per seconds divided by seconds is going to give you meters per second squared, which are the units of acceleration. Okay, so that is number 1, A. Next part, B. Find acceleration from t equals to 2 to t equals to 8. So from here to there. And we actually saw from the moving man simulation, the person was moving at a constant speed. What's the acceleration when you're moving at constant speed? It's 0. He's not accelerating at all. And if you take a look at the slope is not changing. There is no slope. It's a flat line. So the acceleration here is 0 meters per second squared. And so there's a couple of ways you can understand, you can find that the acceleration is 0 meters per second there. Last part, the acceleration after t is equal to 8 seconds. So we're looking at from here to there. The acceleration after t equals 8 seconds, and again we're going to look at the slope, and I'm going to do rise over run. And it's always a better idea to take 2 points as far away as possible on the line to help you get a more kind of precise value. Anyways, try to use 2 points as far away as possible. So I'm using these two. So it's right there and right there. How much is he rising for? He's going from -4 to +3. So he rises 4 up and 3 more, total of 7 meters per second. Divided by the run, and this is positive, don't forget, because we're going up, we're rising. The value of your velocity is increasing. His time is t is 8 seconds to, that's 10, 12, 14, and one more 15. So that's 8 all the way to 15. Many of you are going to make the mistake, oh, it's 15 seconds. No, it's not. It's the difference between 8 seconds and 15 seconds. And that is 7. And that works out very nicely. 7 divided by 7 is 1 meters per second squared. Okay, so now we have all your acceleration values. We can now graph this on our acceleration time graph. So, and again, I'm going to graph it just like the 3 sections here, and notice that I've separated the 3 sections of your graph based on the 3 questions to make it easier for you to interpret. So let's start with t from 0 seconds to 2 seconds, where the acceleration is -2. Let's graph that. So right now we're actually doing question H. Just to make the flow of the understanding of the motion easier. Okay. -2 meters per second squared from 0 to 2 seconds, which is just here. And the acceleration is constant. It is not changing. It's always -2 meters per second at 0 seconds, 1 second, and all the way at 2 seconds. So all we need to do is just to draw a straight line. That's it. Because the acceleration isn't changing. It's at -2 meters per second squared. Then the acceleration drops down to 0. So the guy just remains at constant speed. The acceleration is just 0 for all the way at 8 until 8 seconds. And then C, from 8 seconds to 15 seconds, his acceleration is 1 meters per second, also constant of 1 meters per second. You might be thinking, oh, well, what about the in between these lines? Should we connect them? Honestly, for me, I'm not going to be too picky about this. Dotted lines work, or just leaving it is fine. But you might be thinking, well, how can you really change your speed? How can you just suddenly stop accelerating all of a sudden? And you're right, in actual life, these lines here in between should be a little bit more rounded as per se, so as to show the gradual change in the velocity. You can't just change in a split second. I mean, it's very difficult. You know, it's a gray area. So I'm just going to say for your acceleration between these lines, dotted lines work, not putting anything there is fine. not going to be too picky. But if you're thinking to that deep level, good for you. Anyway, sorry, that was my ramble, and I think that will be all I will do for this video, which is going over the acceleration part. Please watch the next video with the link down below or maybe on the side for part 2, which I will go over the displacement, questions, average velocity, and drawing the position time graph. Thank you for watching, and I will see you back.